What I'm interested in doing, if we want to take a break from SOFP, is the paper that Sergey found a little while ago, the functional collection programming with semi-ring dictionaries. I I think I know what all those words mean, but when I read the abstract, I don't see how they would be putting those things together. So I'm kind of intrigued.
Could you
Uh,
copy the title in the chat, or it is in the Slack, or
it's
maybe?
in the Slack, in the Science of Functional Programming channel, Sergey's post of September 30th. And so I haven't looked at the paper since Sergey posted about it, but I have been intrigued ever since I saw that and um, kind of like to take a look at it.
Okay.
Is that about effects, or that's just something
Uh,
that something else we would be interested in?
right. I think it falls in the something else category. It is not directly on the line of topics related to SOFP, but
Okay.
I am curious to know what on earth they are talking about. So while we're at it, I have to leave a little bit early because once again, I have another meetup immediately following this one. So maybe we should choose a date for the next meeting. So 2 weeks from today would be the 16th of December. And so does that conflict with anything?
For me, it's okay a date before Christmas, but in Christmas, I'm not available.
Right.
Actually,
We'll probably want to take like a month's break after that and meet again in the middle of January. But if the 16th of December is okay for people, then
it
could
was for me.
squeeze in one more meeting.
I think I have an event I'm supposed to go to. Oh, it's not working.
For me, it's okay. In the meantime, I want to look for uh, a book because I wanted to ask you something. If you have here about that, uh,
Okay.
I'm back in a second.
Okay.
Oh, this thing has a link that takes me into Google Calendar and all that sort of stuff. It just doesn't help a whole lot. Oh, yeah. No, I can't do the 16th.
Okay. Well, then the next two
Sorry.
weekends are the 23rd and the 30th, which I'm assuming will be bad for people.
Yeah.
Yeah.
I mean, if you guys want to meet, I'll just skip it. But
No, you wouldn't want to miss semi-ring dictionaries. I mean, at least surely you want to find out what they are. So
okay.
I'm thinking maybe how about the 13th of January?
Not the 6th.
I don't know whether anybody's going to have an extended New Year's week, something.
Hmm.
But
Why
actually,
is my mouse being weird?
it's possible that my cousin might come to visit at some point in the you know late December, early January timeframe. I doubt that it would run as late as the 6th, but maybe. So I'm thinking the 13th would be good and safe, and
Okay.
we'll be all holidayed out by that point.
Holiday out. Yeah. Okay.
Yeah,
13th of January.
13th of January.
Right.
Fine with me.
Okay, let's schedule it for then. Yeah. So.
What
meanwhile-
about the 11th in the other track? Do we have a paper for that?
Oh, yes, of 11th of this month. We don't have a paper yet, but I guess my assignment once we finish this meeting is to find us one. Unless you have a one that you would like to propose.
No, I was wondering if maybe Sergey would know. He might, because he's worked a lot with effects and
Yes,
yeah. So maybe when he comes back, we could
we
check
could.
with him. And what happened to my Zoom window? Ah, there you guys are.
Quickly create a version or create a meeting for next time.
Does the other track, what's the emphasis on for you guys there?
So the emphasis on the other track generally is how are dependently typed programming languages implemented.
Okay.
And so there are a number of tutorials out there sort of describing the basics. But they always leave the interesting parts as exercises for the reader. So the interesting parts are the parts that make the Curry-Harvard correspondence actually hold in the languages. Specifically, it's the part that enforces the rule that all function applications terminate.
Mm-hmm.
So we've been, I guess, over the past year or 2 years, we've been kind of puzzling out how what those rules are and how to enforce them.
Okay.
So but we're investigating a side topic this week, which is if you wanted to extend a pure functional language with an impure imperative language, how would you do that? And so there are a lot of papers about pure treatment of effects. So monadically or otherwise. And so that seems like a good place to start on that question, although it might not give us exactly the answer that we're looking for.
Okay, I have to go to visit my grandmother now.
All right.
My question was about the concept or the term types, but from model theory rather than from type theory. I was studying model theory for a while. Um, I came into this term, right? The notion of saturated models and omitting types. And I'm wondering if it is related with the term type from type theory somehow or not, or I'm strong. Actually, I don't like the definition of type. I read in most books sources. So I believe that it should be a kind of a closure relationship when we define a type, and I don't know. If you would like to take a look, for example, at this Wikipedia entry later on, you could read a little bit about that and think if it is related somehow. Actually, now I tend to think about all mathematical structures as models. So I don't see how something could be out of these kind of definitions. So I will copy the link. It is just a Wikipedia entry of the. Let me copy it.
Uh,
Right. I am copying.
okay.
Wikipedia page on model theory, is that what you're talking about?
Right. The link is on the chat. It is the Wikipedia entry on type, but from the model theoretical point of view. Type how to say underline parenthesis model theory. Yeah.
Hi, everyone.
Hi, Andreas.
Hello.
Hi.
Andreas.
I will go to see my grandma now.
All right. Well,
See you
say
later.
hello from us.
Right.
Can't start my video. Don't know why.
Hmm. Oh, well.
It's blocked.
Okay. Hmm.
So it's fine for the rest.
Yeah.
Okay. So free type class constructions. Shall we dive on in?
Sure.
Sure.
So I have not read all of chapter 13, but I have read the first part up to about 13.5. And so this is kind of an interesting, Sergey is telling an interesting story here where you start out, you want to have a library that is an internal DSL for something that does something. And Sergey goes through sort of the stages that you might pass through when you're building this thing.
And I guess part of the point of building it is that you're not just doing the math directly. You're building a structure that says what math to do or what program. You're basically building programs.
Right. You're coming up with a little command language, and you want to have express these commands in such a way that you can interpret them and actually carry them out. And so he goes through sort of design that just kind of lists the possible commands, and then he refines that a bit by enlisting the type system to ensure that you can't construct a command that doesn't make any sense. And then to take care of the fact that when you're carrying out these commands, you may in fact want to do more programming language type things like binding variables. And so he comes up with a way to bind variables within this command language. But that, of course, gives you something that looks just like monads. And so then he refactors his solution to explicitly be monadic. And then he does a couple more steps where he factors out the common monadic code between different monads, and finally boils it down to a completely generic monad, which is the free monad. And then he discusses the ways in which free monads could be implemented and how those implementations correspond with the monadic laws. And then he goes on to do the same sort of thing for the other type classes that we've been looking at, like monoids and functors and so on. And so
Haven't gotten there.
Yeah, this chapter has more of a narrative feel than some of the material we've gone through, and that there's a sort of steady progression of ideas, all seeming to trend in the same direction of increasing abstraction. So, anybody want to share the book?
I guess I could. Okay. Let me move you guys back over here. Right. So you're seeing it, right?
Yes.
Good. Right, as you were saying, he does some examples, this program that can read files, and it has ways of implementing, I guess interacting with the underlying Java or whatever, or underlying Scala to read files like here and get paths from strings and things like that. Then he has a second example of complex numbers with a bunch of ways of different operations on complex numbers. One thing that when I was going through it, I found a little confusing is like that here, I don't know if you can see this, phase takes a double, but down here, when he turns it into a type class, it just takes one of these complex programs. And similarly, rotate, I think phase returns a double and rotate takes a double, but it doesn't show up here. He fixes it later, but it was just, why is it like that? Anyway, it turns out that you can, because these complex numbers have doubles in them, you don't have to actually pass them directly. You can get them out. You can use your complex number to carry them. And then stage 2, basically type safety. So now it kind of fixes that. So instead of prog file, you now say what kind of thing it returns. And so now phase can return a double, and it can, well, still rotate, still taking no. What is a phase? I don't know. Yeah. Yeah, it takes a phase. Okay, and then implementing bound variables, as Adrian said, is about, in some sense, it's really about running external functions that you can, in your program, you might want to get some data from somewhere else and bring it in. And so you can use the fact that, well, you basically use flat map to do that. Eventually he says that. I don't know where it is, but yeah, so you can like run something else. You can run some external function on, you know, your data, and then bind that up, and it all works. So it's not
Right.
flat mat, it's bind.
Yes, but as
Which-
soon as you see that he has named something bind, you can tell that monads are about to come up.
Right, right. And kind of flat map and bind are two different ways of expressing the same concept. And then, yeah, so now he is defining flat map and map to get it be even more monadic, and flat map is defined in terms of bind, and map is defined in terms of flat map using one of his identity laws. And oh, I guess also in stage 3, he somewhere he generalized val to take any kind of data. Yeah, so here val is now polymorphic. It's not just returning a prog file or whatever, it's returning any A. So you can use,
A profile can basically wrap any type.
yeah, into a profile. Right, right. And let's see. And then step 5 or stage 5, he's refactoring to use the common code. See, I think, did I have notes about? Yeah, so basically he factors things out. So I guess this is the way it looked before, and now for like the program, file program thing, you now make it take, well, I guess it took a parameter before, but now he's calling it prog file C, I guess for constructor. I don't know why he picked C, but the idea is you separate it out into 2 parts, the generic part, which we're going to get to, and the effects specific part, which is given by prog file C in this case. So it just has the path and read operations that are specific to this program thing, and there's a run file C that basically allows you to run them. And then you have the same trait prog file that you had before, without the C, and then there are these case classes for val and bind and op, which I didn't see at first. I didn't see op because it was on the next page, and it's like, where is he? Anyway. And then there's basically a runner for this that deals with val, bind, and op, and it basically takes a runner, the run file C, to deal with the op. So it basically passes in no, okay, not in this case. Run file C is just static, so he's just calling it directly. And then he refactors prog complex the same way. And then he says, well, notice that, the val, bind, and op are all implemented the same way. So let's just factor that out. We'll call it monad DSL. It takes the effect constructor as an argument and defines flat map and map. It's kind of along the lines that we talked about before. There's a pure operation. This is the companion object to the monad trait. So you can have a trait with that name and an object with the same name and put related stuff in the object, the companion object. So he's putting pure in there, and that's the thing that just returns a val. And then he has the case classes for val, bind, and op. And they basically just implemented along the lines that he's had above. Well, they don't do much. They're just basically classes that hold data, and then the runner is the thing that takes an effect runner, which takes in the effect construct, basically takes the specific thing, whether it's the file program or the complex program, that's passed in as a runner that takes an f of a to a. And if you get the op case, then you just run the runner on that op. And val just returns a, but bind basically runs basically going from the inside out. It basically runs the runner on the PA argument to bind, and then applies F, and then runs that. And this .f confused me, but I won't go into it unless somebody wants to. I don't know why you didn't have just a bind take two arguments in its constructor. So yeah, that code, go ahead.
Yeah, it does, but they're curried.
Right, and I guess you can't match on curried arguments for some reason. That maybe if they weren't curried, then you could match, right? You should be able to.
Yeah.
So instead, basically this is an anonymous function. There's no lambda variable that's present here, but you can get it by using this bind, this at syntax. Basically, you're saying, bind to whatever the variable is that's coming in. The value that we're casing on will be bound to bind, and then we can say bind.f because it's there's too many binds here, but anyway, then you can say bind.f, and that will give you the F field that was in there. So yeah, as you pointed out, as Adrian pointed out, bind is curried. So the first argument's passed in, but the second one is a val field. So this val here makes F be a member of this class. And so you can say bind.f on it. But this code doesn't compile because it's not generic enough. So instead, you have to have a runner that's generic. And you can define your runner for complex numbers by defining the polymorphic run to just basically be the function run complex that was defined above, and same thing for run file. So you're just basically wrapping the runner in the effect specific runner that you had before. You're just wrapping it up in this runner class, and that makes it more generic. And he has a quick thing that in Scala 3, you can write it more simply. But I think we're going back to Scala 2 here. And now we're defining run for the monad DSL. Because this run takes I wish he'd called this like runner C or something, because it gets kind of confusing in here. And in fact, there's run runner and runner dot run. And sometimes I think those two things are actually the same thing. You can kind of do extension methods sort of along those lines by saying, if you have runner.run and you don't see that run is a member of runner, you can then flip it around and think of run, look for a function run that takes runner as an argument, and then do that. So, but that's not what's going on here. Scala doesn't work that way.
There's another run involved.
Yeah, so there's the run that's wrapped up in here, and then there's the run that we're defining here. So they're two different runs. But basically it works along the same lines. Val just returns an A, op runs the runner specific run on that operation because it knows how to deal with the operations. And then bind basically runs the runner on the first argument and then applies the F argument, the second argument to that, and then runs the result to get out an A. And that's, yeah. And then, right, and then as Adrian said, he kind of goes into this. Yeah, goes into this more generic. So first he says, okay, here's the general way that we're doing this. You create a sealed trait for your effect constructor, and then you can have, case classes for each of your effect specific operations, or I guess, is that right to say effect specific? I guess, yeah, DSL's effect constructor. I don't know what the word effect really means, so I fumble over it sometimes. But anyway, so you're creating something that's specific to your set of effects, which before was the file operations or the complex operations. But in general, you're just going to have a trait and you're going to define a bunch of case classes for that trait. And then, and here's an example for prog file. And then you're going to define a runner. And then, right. And then you're going to have a runner for your effects. And then you use your general monadic DSL to glue it all together. And Sergey's back.
Yep. Hello, I'm back.
Hi. We're just kind of going through the first
So to
5 or
comment
6 steps.
on your question about effects, right? So essentially, it is anything that is not directly expressed by the DSL, right? The DSL says find a file in this path, read it, but the DSL doesn't actually read it. It just says that it needs. Well, it says something along those lines. It has a constructor whose name is read. So to us, it's clear what we want. We want at this point to read the file, but the DSL itself doesn't say that. It's just a case class, right? So it's something that needs to be run with some other code, and it will be run later. It will not be run right now. So the value of DSL type does not run any of that code itself. So that is what I mean by effect. So it's kind of you are denoting the intention of doing something, which usually is going to be a side effect. Usually it's going to be some kind of real world operation, but not necessarily. It doesn't have to be. But it's something that the DSL does not do. So what DSL does, it binds values to different scopes, and it builds this big data structure that expresses what you want to do. And the DSL
basically
can
building a program, right?
Yes, the DSL program, yeah. So the DSL can combine programs. The DSL can express bindings of variables to results of programs. And the DSL can do other things, like you can say inside the DSL, you can do pretty much anything you want, except that you don't want to do those things. You don't want to do effects there. You want to postpone the effects. And so the effects are those things that you don't do in the DSL. So for example, you can express in the DSL that if some condition holds, then you read the file. Otherwise, you don't read the file. Right? So you can express that in the DSL, but not the reading itself. So that's how I think about it. So effects, and that's why you need an effect constructor and an effect runner. So effect constructor is a functor that will describe those effects, but if only the effect runner knows how to run them. And until you apply the runner, the DSL program does not run them. So this is what effect means, really.
So you're basically separating out the effect specific parts from right what's in the DSL.
Yeah, the DSL
monad is just basically pure and bind and map and flat.
Well, you can have other code in there. You can have other code. You have if then else in there. You can do other things. You can put values into tuples and so on. You can do all kinds of things, but you don't do file reading and file writing and those things. You specifically don't do that inside the DSL because you want to express the logic in those things separately from doing those things. So you want to express your business logic separately from executing that business logic. That is the point. Now, what is that business logic? Depends on your application. So it could be file reading, it could be graphical user interface, it could be something else. Complex numbers, for example. You might think this is frivolous to write such a thing, just to multiply complex numbers. But imagine that instead of complex numbers, you have massively parallel data structures with billions of elements so that don't fit into memory. You certainly don't want to run that into your code. You want to denote that, and then some sophisticated runner will distribute this work among thousands of computers later on. And that will be just the runner's job to do that. And your job is to express the business logic. And you say, well, read a billion numbers into memory, but you don't read them right there. That would be madness, right? So like Spark does this kind of thing. You write a Spark program, and it looks like you have this huge array on which you perform operations. But actually, you don't have that array in memory. It is too big to fit in memory. So you are denoting those operations. And then there will be this sophisticated runtime that parallelizes your code. So that's similar. I mean, Apache Spark does not work using the free monad, but it's a similar idea that you want to express business logic. Your code looks like you're doing it, but you actually aren't doing it. Some runner will do it.
Right.
And the interesting thing that I found is that you, in these steps, right, stage 5, stage 2, stage 3, you kind of force yourself into writing a monad. You didn't know that you were doing it. You wanted to have a type-safe language where you bind variables. That's all you wanted, really.
Or the binding variables is kind of about running an external thing, right? To some extent.
Well, you say when this is run, and then it gives you the result, and take that result and do something later. Right?
Yeah. Right.
So just because you wanted to express this kind of thing, you turned out to need monads. That is, and this particular free monad is kind of forced on you. You did not start out with this. You arrived at it organically, just from the requirements of what you needed to do.
Yeah, I thought that was a good progression.
So this was, I mean, this is a tutorial that I believe was missing in many presentations of free monad.
Right.
But I mean, you can, but also once you do it this way, I made this comment that laws don't hold.
Yeah.
So once you arrive at the free monad this way, then you find that it doesn't satisfy the monad laws. And it only satisfies laws after you run it. So this is a surprising thing, because if you start with the free monad, it will, you know, from the mathematical point of view, it must be a lawful monad. You won't arrive at this step in this code. You won't get this code, but this code is totally fine, and it could be better in some ways than the theoretical code that you get if you start with the theoretical construction of a free monad on a functor and write the code corresponding to that. So, and this was kind of a very.
I was just going to say it kind of feels like a form of extensionality. You know, the two things aren't syntactically the same thing. They're not the same structure, but like when you run them, then they are. They give you the
Yes,
same result. It's sort
yes,
of like
right.
extensional functions can have two different functions, but when you apply them, they give you the same result. So they're extensionally equal. So that's kind of what's going on here.
Right. Yeah, this is surprising to me. This was surprising that
Yeah.
I get some structure that doesn't satisfy the laws, but that's not a problem. That's okay, because miraculously it does satisfy the laws after you run it. Now, the entire development that's going to be in this chapter, it's not yet written up, just to explain why that is so. So I have previously I talked about this in different meetups, that there is a theory of free type classes that do not satisfy some of the laws. This is if you this is kind of a theory that is missing to explain why programmers are writing this and nothing happens, nothing bad happens. Programmers write free monad or free functor or free something else that doesn't satisfy the laws, and that's okay. Because miraculously the laws will be always holding once you run it. And I proved it for some simple cases. I cannot prove it for monads, for free monads. It's not, I mean, it's technically complicated, but I proved it for simple type classes like monoids and semigroups. That you can have, indeed, you can have this code, this kind of code that intuitively does the right thing. It just doesn't satisfy some of the laws. But when you run it, it does satisfy all the laws. So since you don't care about laws until you run it, you don't actually use these intermediate values, you always have to run, then it's okay.
Right. So it sounds as if you want to examine whether these structures obey the laws at a quotiented type where the quotient involves running it.
Yeah, something like that.
Right. Then you restore the usual formulation of the laws.
Yes, but the thing is, it always worked like that. There's no accident here that so I'm saying this is a recipe, right? It's a recipe for how to do a DSL. This recipe will always work. There's no accident in this, and not only for free monads, for free anything else, exactly the same problem, the same situation. And so yeah, this is an interesting thing that I discovered, that yeah, laws are still there somehow. They just you don't see them at the level of DSL programs, but they're still somehow there. So,
but then you kind of then go into saying, well, maybe we could restructure things so that, for instance, flat map does satisfy the law,
right?
Because it just basically internally doesn't create the nested structure. It's just creating the right structure.
Yes. Yeah. Right. Now you can you can refactor so that laws hold already at the level of DSL, and I give examples of that, and you get a different formulation of a free monad or free other type class, and usually it will have fewer case classes. Usually you will eliminate case classes because of the laws.
And so is that what the different encodings are? I haven't gotten that far. There are different ways of creating the free monad that does satisfy the laws, or some of the laws.
Well, so I call them encodings, right? So here's the thing. There are 3 examples, right, on this page that you're sharing. There are three examples of a free monad, which have been presented at talks as the free monad, right? So,
The
yeah, this is the free monad. Every one of them said that. This, what is the free monad? This is what the free monad is, and the code is different, and it's not equivalent. I mean, it's not just a trivial equivalence. So, and you see the last example it has 3 case classes, and the previous example has only 2 type classes, and so that's anyway, this is just an example of different encodings, and in fact they all satisfy different subsets of the laws. So if you start with the one that satisfies no laws, you impose some laws and refactor, then you get a different encoding, and you again impose more laws, you get another encoding. So these are, now I'm just giving a kind of a derivation of how you can get from one to the other.
So
but
I have a question.
Yeah. Mm-hmm.
I mean, logically, is it true that logically there really is only one free monad, in the sense of the free thing, you have certain operations and you need to be able to do all types, reasonable combinations of those operations, but then you have a bunch of laws that kind of bring it down. So the free monad would be the most general thing that would allow you to do all the operations and would satisfy all the laws. So is that formulation enough to say there is only one, a unique one, or is it not that strong?
Yeah, right now, yeah, I can answer that. You formulate a free monad as an initial object in some category. I'm not going to go into details right now. Some initial algebra or some functor, whatever, doesn't matter. So then it's unique.
Okay.
Right. The question is,
what is initial?
That? Yeah. And it's initial, right? So any other initial will be equivalent to this one. So that's unique. But you are actually free to choose a subset of laws. That is the thing that is not obvious. So when you say I want a free monad, then you kind of force yourself into obeying all the monad laws, because you just said monad, right? So if it doesn't obey some of the laws, it's not a monad. You take a category of monads, and there isn't a single object in that category that violates some laws. So you kind of excluded right away any of this code here, other than the first one. I believe the first one is satisfying all the laws, but the other two don't. Now, if you say I'm interested in something that has the operations, but it doesn't necessarily has to satisfy the laws until I run it. When I run it, yeah, it does, but not before I run it. If you start formulating it like this, then you are free to relax the laws. You can free to forget some of the laws, and you say, what is the initial object among those that satisfy only those laws but not others? Then you will get again a unique one, but a different one, which is kind of less lawful, and you will still have a unique initial object, but just in a different category, slightly larger category, because you have allowed objects that don't satisfy some of the laws. And I have an example of this. Unfortunately, I haven't written all of this neatly. But example is monoid. Monoid is much simpler, right? Monoid has
I
also
go
three.
down here, or
Yeah, you can go. I'm not sure if I already wrote it up here in this version probably, but let me take a look at this. So yeah, so those are
13.3.3 is free monoid and it's partially lawful encodings.
that's right. That's right. So this is a kind of a simplest situation where you can write down everything explicitly. So first thing you do is you follow the recipe, right? So I guess follow the recipe and you get the one that is on top of the page. At the top of the page, you have three case classes, and you're done. So, but what do you get? Actually, you get a tree, a
what
binary
is wrap
tree.
for?
So wraps the external, the effects. So you're saying I have a type T, which is not a monoid, and that represents the effects. And
okay.
so it's the same as in the free monad case. You have a functor. It is not a monad. It represents the effects, right? Reading a file, writing a file, and so on. And then I want to make it into a monad, so I wrap it into some more stuff, so that I have a monad. So it's similarly here for the monoid. So you have a type that is not a monoid, and then you wrap it into something, and that becomes a monoid. So, but if you look at the type, it is just a binary tree with leaves of values 1 plus t. So it's actually an unevaluated tree of operations, of monoidal operations, which wouldn't satisfy any of the laws because it doesn't reduce anything. If you have, so 1 plus t, 1 means the empty element of the monoid. So if you have everywhere ones, it doesn't reduce this to 1. Right? It's still a tree with a lot of operations, just everybody empty. But so it's just an completely unevaluated tree with even the associativity is not taken into account. So you know, the tree is not rebalanced in any way. It's just like this. And yet this thing is so what I call FMR, a free monoid in the raw tree encoding. So this is a kind of a completely raw tree. It has nothing, no knowledge of any laws. And yet, if you run it, you will satisfy all the laws. Because of the way it's organized, of course. But
okay, I have a question though, because when you run it, you're evaluating it, so you're reducing it to a single value, aren't you?
Yeah.
So what does it mean that it satisfies the laws when you run it? Except that, A is equal to A.
Run both sides of the law, and you get the same value.
Same value.
Yeah.
That's what you mean by it satisfies the law?
You have a law, right? For example, empty plus x equals x, right? Now, empty plus x is a tree, which is not equal to the tree for x. Right?
Okay.
Now, so the law is not satisfied, but when you run it, you will evaluate them to the same value.
But then what does it mean that it satisfies the law? Because the law is not on the base type. The law is on the structure, right? The monoid. I mean, the monad, for example, law is relating the monad, let's say, T composed with T can be reduced to T, right? Not the underlying. So I'm a little bit confused there about what it means to, because if you have a free, then there is no reduction, right? There is no simplification you can do. So I don't know. Okay, what are the laws that a free monad is supposed to satisfy besides the fact that, oh, okay. I'm a little bit confused here about what it means for something to be free in a like a free monad, and then how that relates to the monad laws, like the identity and then the composition, right? T composed with T maps to T, for example. Because if you have a free over free, then you can reduce it to a single free by substituting a subtrees into all the leaves, for example.
Yes, yes, right.
Right. So that's the law.
That's
right?
not the law that we usually talk about when we talk about
Okay.
monoid laws.
I see. Okay.
But let's look at the monoid. So what does it mean to run a free monoid? It means you need a function that, first of all, you need an actual monoid result type, right? So you map this entire thing into M. So M must be a monoid. So you need to map T into M somehow, doesn't matter how. So if you look at the type signature of runner FMR, then you see you need to have a monoid M. Then you need to have a map from T to M. And then you can map the entire free monoid of T into M.
Yes.
So that is the runner. That is what it means to run. You map this DSL program into a final value of type M. Now, type M is an actual.
So even there, I'm sorry, it's just like you were saying, there's no semantics in the tree, but the runner basically has all the semantics that basically implements this monoid, and only after applying the runner do the laws hold. So it's kind of a different formulation of the laws, but it's sort of
so what I'm saying is that
direction.
For our program, it is enough if laws hold after applying the runner. So we do not actually need to impose the laws on the DSL because we will never suffer from any violations of those laws if they're invisible after running. So what I'm saying here is that the free monoid, it has three laws. You can select any subset of these three laws, and you can say what is the initial object in the correct category corresponding to monoids that are not actually monoids, but they just satisfy partially some laws, but not others. And you will obtain a data structure that is unique, and it is the initial object in that category. And so this one is the initial object for the monoids that are actually violating all of the laws. They may violate any of the laws. They're not constrained by any laws. They must have the operations, but no laws. So for those, this is the initial object. And the non-trivial thing is that it's okay to do that kind of thing. It's okay to relax the laws when you're talking about free objects, free type classes. It's okay to relax the laws. It's not necessary to keep all the laws. Now, the one that is completely lawful is list of T. List of T is the free monoid on T, which satisfies all the laws. And the tree of 1 plus T is the one that doesn't satisfy any of the laws. Now, if you scroll down, maybe you'll see other examples. I'm not sure if I already wrote them up. Maybe. Yeah, I did. 1, 2, 3. I have several examples here. So yeah, that's right.
4 at least.
Yeah, I have 4 different encodings. There may be others, certainly, because for example, I don't say, well, I want to satisfy the left identity law, but not the right one. Well, I could think about doing that, but I didn't. So yeah, so if you look at the first encoding is none of the laws. The second encoding satisfies the associativity, but not identity. The third satisfies identity, but not associativity. And the fourth one satisfies everything. So this is the kind of thing that
Because you implement it as list.
yeah. Well, it mustn't be. I mean, it's unique, this thing. So once you say which laws you want, you have a unique, a free object. Now, from the usual category theory formulation, this is wrong because you need to satisfy the laws. But now I say, okay, well, I don't care as long as I run into, if I evaluate this into a completely lawful monoid, I can prove that laws will be, so all law violations will be hidden, will be completely invisible. And this is an interesting thing. So the standard category theory formulation is that you can have a unique free something. And the only difference is that I relax some of the laws. I allow some of the laws to be violated because I know that this is okay. These law violations are hidden. They're going to be invisible once I run the program.
So for all these encodings, they're all extensionally satisfying the laws in the sense that I was saying before.
Right.
Now, can you derive for, or you just have to like come up with it? Do you know what I mean?
There isn't, no, I'm not saying there are only 4. Also, there isn't a very easy way of deriving this.
Right. Okay.
It's kind of I showed how you kind of come up with it. You try to impose the law. You start with what you can derive is the first one. The first one, which is completely lawless. That one you can derive. That's pretty easy. I mean, you can derive that mechanically. It's a monad of a certain kind. Anyway, you can derive that. The other ones you can't really mechanically derive. It's not easy to impose the laws. You can start with the first one and see what is the law violation, and then you kind of massage the case classes until it disappears. That's what you do.
Right, but it takes intelligence to do that.
Yeah, I don't have a procedure.
Yeah.
The first one is mechanical. The others are not mechanical, and mostly because it's not easy to encode what it means to satisfy a law. And then do something. And law is not a functor. Law is not a. It's some equation between
it's expressions.
It's a quotient between different, difficult things. The equivalence relation is formulated as some equation, right? So what do you do? Some operations, combination of this operation and that operation must be equal to that operation and this operation. What do you do with this? So how do you actually compute the type that results from this? There are some research papers in this direction, but not many. Quotient, how do you prove something about quotient types with laws and so on? I haven't found any recipe for coming up with this. So my best recipe is you mechanically derive the first one, which satisfies none of the laws, and then you write down the laws that you would like to satisfy to see what is being violated and which case classes are at fault. And maybe if you impose the law, you can get rid of those case classes or rewrite implementations or something. And then you proceed in this way.
I was just thinking about some stuff we had talked about, maybe in the other track, where using homotopy type theory, there's a way of doing quotients, because you get to redefine what equality is. So you can define
Mhm.
equality to
Mhm.
basically implement your equivalence relation.
Mhm.
But
Okay, well,
anyway,
does it help you write code?
I don't think so.
No.
It gives you a way to write the code and have it turn out to, I think it would turn out to satisfy the laws, but
It gives you a way to write proofs
Right.
rather than code that does stuff.
right.
Yeah, but then I mean, if I wanted to come up with
Yeah.
encoding number 3 in here, what do I do?
Yeah.
I have identity laws, but no associativity laws on the monoid. So
Mhm.
how do I come up with this? Anyway, that's all I wanted to say. So yeah, so if you scroll down, maybe we'll see what happens then. So there are 4 encodings that I give, and then I say, oh, show injectivity of those transformations. Oh yeah, so it turns out that well, you can convert one to the other, and then they're always injective. So the encoding that has more laws can be injected into an encoding that has fewer laws. So it's an injective map.
Okay.
Which is kind of interesting, and actually, so I based on that I generalized to arbitrary type classes that you can have encodings, and then you have an injective map, and it kind of it allows you to prove more quickly that you found the correct encoding if you have this injective map. So, but this is kind of clear, right? If you have something that doesn't satisfy the laws, you can always inject into that the thing that satisfies the
Something that
laws.
does.
You just choose equivalence class arbitrarily for that, and you inject it. When you quotient back, you get what you had. It's clear, right? So in this case, it's kind of not obvious that we are quotienting one type and get another. But this is essentially what it is.
You're essentially getting a kind of subtype relation
Well,
here
quotient
between
type.
the different
I think
encodings.
yeah, I think the quotient type is the right formulation. So what you say, I want to impose the law. That's the same as you say, I want to take a quotient. So you
Right.
take an encoding that doesn't satisfy the laws, you impose the law. It's just the same as to say I take a quotient and I get another type. So how do you actually compute that other type? Well, you look at it and think.
Yeah. I guess what I was thinking was that like F1, if you think of that as a type, it's the most general because it's sort of the super type because it has no constraints. And then you go down to F2 and it's not a direct subtype in some sense, but because of your injectivity, anything that's an F2 can be turned into an F1. So in that sense, but yeah.
But this is a general situation, right? If a quotient, you can always inject it back into a non-quotient initial type, and this is what we have here.
Right.
So that's yeah, that's about all. Now, okay, sorry, I interrupted. You wanted to say something else, maybe, Peter?
No, I think that's okay. That's good.
Right. So okay, so let me then explain what is going to be in this chapter when it's finished. I don't know when it's going to be finished. I have a dilemma right now. I'm not sure how to proceed because it turned out, so there is stuff here that is mainly documenting what are the known encodings for free functor, free applicative, free this, free that. which is okay. But then, so for example, what if you want to have a free monad on a pointed functor? Right, so you already have pure. You just need bind, or right, flat map. So you don't want to make again a free implementation for pure because you already have one. So how do you quotient by that? So you are having a free monad on a type constructor which is already partially part way towards the monad. Something like this. Now, then, so my dilemma right now is that I want to prove this main statement about free type classes, that in a certain way you can easily construct a free type class that satisfies some of the laws, but not all. And in order to prove that, I need some property that I thought would hold for any traversable functor, but it's not possible to prove using the laws of traversable functors from the previous chapter. And in fact, then I started to dig into that. I found that the laws are not complete. Maybe we already discussed this in the previous meetup.
We did mention it, yes.
Yeah. So there is one more law that needs to be assumed or postulated in order to have the property, for example, that zip with index generates different indices. This is a ridiculous situation where zip with index, the function that by definition needs to index the values by different numbers, right? Not by the same, right? But you want to prove that it does. And it's impossible to prove. So, because you don't have enough laws. And so now either I will have to update my entire previous chapter saying that there are now 3 laws of traverse, and then I have to prove every time one more law in every construction. And then I have a hope of proving the property of zip with index. A lot of work, which might be interesting, but I don't know. Or I find a different way. So essentially what I want is the following. I want to show that any polynomial functor has has finitely many values that can be numbered. That's all I want to show. That's all I need. I need to number the values. I need to say that any polynomial functor, even recursive ones like lists of trees or whatever, any value of that type contains a finite number of values of type A, let's say. We have a list of A, tree of A, and so on. And these values can be numbered, and the labels can be chosen so that they do not repeat. That's all I want to prove. Now, maybe I can just prove it directly. And if so, I can finish something, and then I don't have any more questions for this chapter. Church encodings. I don't know if I want to include church encodings. I don't remember anymore why I wanted to do it. I spent a long time studying this, and I don't know anymore why it is relevant in this chapter. The only thing that's maybe relevant is this so-called final tagless style. I don't know if anyone here heard of this. Yeah, you've heard of it, Adrian. So
I have heard of it, although I can't say I've done anything with it.
Yeah, I mean this. I thought it would be, well, first of all, I thought it would be useful to explain what it is briefly. And briefly just means church encoding of a free monad. So it's just an equivalent type encoding of a free monad. And then, okay, well, when you say that, you have to explain what church encoding is, right? What is a church encoding of a tree, right? Because just above we had a free monoid, which was a tree. What is a church encoding of a list of it? What is a church encoding of a list? So how do you write it? What is that type? And then I started, so I have in this chapter some proofs about church encoding. Okay, well, is it really interesting? I don't know. But I mean, to me, church encoding is interesting because it allows you to convert recursive types into non-recursive types. And because church encoding always encodes the least fixed point.
It has recursion built in.
Yeah, it has recursion, but it's safe. It never loops infinitely.
Right.
Because it's the least fixed point. And because it's the least fixed point, then you can hide recursion in the church encoding. And you can have a type like list or tree, which is usually defined recursively, but church encoding of that is not recursive. And the price you pay for this is performance. For example, if you want to determine if a list is empty or not, you have to traverse it. So you have a list of 5 billion elements, and you want to know if it's empty, you will have to traverse it, and then you will know. So this is how church encoding works. So you can do everything that you like church encoded list, for example. You can do everything you do with a list. You can do fold, pattern matching, but it comes at a price. So performance is not going to be great.
Because it's going to do something like, basically the church encoding, you give it the case for when it's empty and for when it's not empty, but it will do the recursion for you. So it will go down the entire tree saying, are you, and then get down to the bottom and it will say, yes, I'm an empty tree. And yes, I'm an empty tree. But then it will say, nope, I'm not an empty tree. And then all those falses will go back up and eventually come out the top, but it had to ask the entire tree.
Yeah, so that is, you can try to mitigate this in some ways, but that's essentially the problem with performance.
Right.
But in a context where this is not a problem, you can take advantage of this. So free monad has a similar problem that if you have deeply nested free monad operations, then certain operations become very slow. So if you have one more bind, needs to rebind everything suddenly, and so on. Now, some of the encodings that I showed do not have this problem, and others do. So that's the reason why sometimes you want to choose one encoding and sometimes another. Essentially, think about it. I think about it this way. Suppose I have a list, but I represent it always as a tree. So how do I represent a list as a tree? Well, it's just a tree that goes in one direction, right? Now, suppose I have some operation on that tree. Like add this a subtree to this. Suddenly, I have to rebalance everything. Because if I just take take a grafting of one subtree to the whole tree, then it will no longer be of this shape. So I have to reshape the tree. So some operations will be linear in the size suddenly, although you didn't think so. So this is the kind of problem. But in situations where you don't have this problem, that's good. So anyway, I have complete proofs of all the properties of the church encoding. Kind of using parametricity. And I thought to put them into here. And now I'm kind of, I took some time to think about this entire situation and what I want to prove and why and so on. Now it doesn't fit here so much. So suddenly I have 10 pages of proofs about church encoding.
You can always make another chapter
Appendix.
or another appendix, yes.
Yeah, I mean, church encoding is a technique that has a narrow application. And one thing that I had is, for example, I mentioned several times a DALL language, DHALL, which is a language where everything terminates and doesn't have recursion, but it does have church encoding. So it's kind of interesting. So you can do lists, trees, whatever, if you want to. So church encoding is then the go-to mechanism for implementing data structures in that language. And yeah, it's slow, but it's not supposed to be fast. This language is not supposed to be running at runtime. It's a configuration language that is run before you start your program to generate configuration. So,
but the church encoding is sort of what you get if you have abstract data types, or
well,
yeah,
what I mean is
because you're not interpreting anything, right? Basically, church encoding just uses variables and then function application, but there's no reduction, right? You're just building up terms. So, and same thing in abstract data type is that you just generate a tree of terms, a tree-like terms composing other terms, and then you don't have an eval yet. So,
right. But yeah, the eliminator for an abstract data type is basically the church encoding.
Mm-hmm.
So I have a question about what you're saying before about the laws and needing to prove that the tags are different for every node, basically. Do the tags have to be like natural numbers, or can they be anything as long as they end up being different?
Yeah, so in fact, it's difficult to prove with natural numbers. It's easier to prove if you say these are just some values of some type that come from a stream of values. And if I consume this many of them, so the paper that I found very useful is reformulating zip as not a function that uses numbers, but a function that uses as labels a stream, an infinite stream of labels, which is kind of a source of unique fresh labels, as many as you want. And it consumes a finite number at the beginning of the stream. And then you want to have an operation that puts them back into the stream, prepends to the stream. So you kind of take out whatever labels you used, you extract them and put them back. And you want that to be equal to the initial stream. So in other words, you want to show that you have consumed some labels and you used all of them, and you didn't duplicate them or ignore them. You used each one of them exactly once. So when you extract those labels back and put them back into the beginning of the stream, you get back the stream that you started with.
They have to be in the same order, so that
the same order, exactly same order,
which basically says that you did in fact encode the structure appropriately.
Yes, you encoded the structure, you extracted them back into the right order one by one, and it turns out this is easier to prove. So it's a stream of things of arbitrary type, and you don't care about what that is, and it's kind of easier to prove like this. But anyway, I'm not sure I want to go into that. It's a very narrow area where, in fact, it's kind of making things too difficult. It's making things too difficult because traversable functors are just polynomial functors that you know, they have to be least fixed points of something. They cannot be infinite streams. So they are always finitary. They're always finitary containers. And so it's much easier just to not to say, oh, it's something that has laws. No, you just say, I'm talking about polynomial functors, full stop. And polynomial functors, you know, you can enumerate things that are inside them, full stop. So you don't first say it's some arbitrary functor that has properties. No, it's too complicated to do it that way. So actually, yeah, it's
be more concrete. Just say, well, they're polynomial functors.
Yeah, I'm not talking.
We know
about
what they are.
And, exactly. Yeah. We know who you are, and we are going to talk about you. So, yeah.
I have another question. In the other track, we're sort of looking at for some papers about how to sort of add effects into a pure language. And it seems like a lot of this is sort of what you're describing. Is there, I don't know, what are we looking for, Adrian? Like some sort of paper that papers that sort of talk about the, you know, like how would you add in mutation specifically or something like that?
Right. Is it are effects necessarily monadic, or are there frameworks for talking about effects that are not specifically monadic, but phrased in some other way?
Right. So, okay, so one thing I can say is that I tried to read some papers about so-called algebraic effects. And to me, nothing they say goes beyond the free monad. It's just in terms of expressive power. Certainly there are improvements, like you can formulate more easily what you do if you have two different domain-specific languages, you want to combine them, or you want to run some effects but not all, right? And so you run some of the effects, but you still have some unevaluated effects. So in this language of free monad, it's not very easy to talk about that, right? So either so for example, you have this F, the effect constructor, right? It has a disjunctive type. It has many parts, many disjunctions, components of the disjunction. Suppose you want to run some of them, but not others. So you cannot really express it in this language, because you're supposed to run from F of X to X. You're not supposed to just, oh, I want to run some of the pattern matching cases, but not others. And others I just keep. You can't keep them. So you need to now define F as a co-product of some F1 and F2, and you run F1, and the result is still a free monad on F2. It's not easy to do that. So effects are trying to make it easier. So you can say granularity. You can say, I run these and I don't run those. Or I run these, but I get some more as a result of running, in addition to those I didn't run, or something like that. So it's essentially improvements in usability for the free monad. Now, there are also non-monadic effects like anything else here, any other free type class will have the same properties. You will still have the same scheme. You evaluate after you have composed the program. So you compose the program, evaluating nothing, and then you evaluate everything. So this, for example, you can talk about applicative effects, talk about monoidal effects, talk about other things, right? So which means that you have, what does it mean that you have applicative effects? It means none of your business logic depends in this way on previous results. So you know, your effects can depend on previous effects, but your results cannot depend on previous results, and effects cannot depend on previous results. So, okay, well, this is a different way of talking about effects, but essentially, how do you add effects? I thought about how I would use this DOL language for anything practical, anything that is not just configuration management. I would have to add symbolic types to it, right, that don't do anything. But when I run this program, my runtime recognizes those types. Right? So, right. So, for example, I would, if I want to compute some numerical function that DOL does not allow me to compute, I would, or print text to the screen, right? So I make a type constructor or something like that, which will be just a name and will remain unevaluated in the program. And my final value will contain this unevaluated thing. But then there will be a runtime that will recognize this name and run the effect. Or I do a free monad, right, which is perfectly fine in a purely functional language with no side effects. You just write this free monad, but the special names of these constructors will be interpreted by the runtime. So essentially, I will have a runtime which is written in a different language.
So are you saying like you'd have a type constructor for like print or something like that, and you would put a string in that type constructor and it doesn't do anything. But when you get around to interpreting or running that program and it got to that thing, it would then have to dispatch to whatever the appropriate code is for printing.
Yes. So the solution is that you would have a runtime which is aware of the effects you want to run. I was thinking about doing this for user interfaces, for example. So the effects in the user interfaces is to show some window on the screen and to wait for user interactions in that window. Some mouse, keyboard, and so on. And then now none of this can be expressed in a purely functional language, right? But you can just have type constructors that you create, and essentially you create a big value which contains maybe functions in it and whatever, but it's just a value, right? So it contains some types, some values, functions, and that's it. That's the result of your computation in this language. So this language computes this value, combining other things into it. And then there is a runtime, which is written in, say, Scala. And this runtime will recognize the names and say, oh, this is the swing with visual component named like this. So I just create that and put it on the screen. And then, oh, and this is a special thing for button clicks. So I will do the imperative Java code for binding some handler, whatever, blah, blah, to catch the button click. But this will be, first of all, this will be a different component. It will be the runtime, which is much smaller. It's completely unaware of your business logic, and it will be presumably easier to implement. You will just say, oh, these types mean this types mean that, and you're done.
So how do you
that,
do the variable binding in that case?
Yeah, well, for the user interfaces, there is a so the way of doing this is that you have a function from the visual component to the variable. So in other words, the visual component contains in it some parts that are marked specially, which are recognized to be variable binders. And so if that part is clicked, no, but this is still a value, it's just a label, right? So it's just a label, but it can contain a function to update the variable. But this function is a pure function, right? So take the old value of the variable, return the new value of the variable. So this function is part of the visual type, the type of the view of the visual window. But part of the type is these functions that update the variables in your program, and the runtime needs to bind this and to run. When the button is clicked, and it has to execute that function and store the new value in the mutable memory. So the runtime will have to be fully aware of all the mutability and the side effects and threading, multi-threading, and everything. But not your user code, because this runtime is written once and for all. And yes, it will be impure, it will have mutability, it will have multi-threading, and so on. But that is a relatively small piece of code, which will just read some value and interpret it as a just like the DSL is interpreted. So I have not, I don't say the free monad needs to be there, but it is one possibility. You can just say, well, there's a special library for this language which has special names, and if you use that library, then the runtime will run effects. So this is a possibility, but again, this depends on being able to express what you want to do in a purely functional way. And so free monad is one possibility.
This is a great discussion. Unfortunately, I have to go get ready for my next meetup. So I'll leave you here and watch the recording to see what I miss after this point. I'll see you all on the 13th of January.
All right.
Yeah. Bye, Adrian.
Bye.
Bye.
Right. So, okay. So that's as much as I could say. Now, what else is still there in this version? Types with existential quantifiers. Now I'm starting into that area. Types with existential quantifiers. If you like, laws of free constructions is this attempt to formulate a general theory of type classes with free type classes with partially satisfying laws. And then essentially, what do I have in the discussion? I don't know. Yeah, I want to prove. So what I came up with is that I need to have techniques for working with universal quantifiers, and I will revisit this entire chapter again to see if I really want this in the chapter or this needs to be in an appendix. Because this is a bit technical. All these things like church encodings depend on this, but none of the discussion that we went through with free monad DSLs require this kind of technique. So yeah, I don't know. But let me just mention that so I wrote up a lot of proofs in this chapter already about the free constructions of type classes, and a lot of that will certainly stay in the chapter. But let me just write an example of what I want to do.
You want the screen or are you
No, it's okay. I'm just writing it here.
Right.
Okay. Essentially, what I want is to be able to simplify any type with universal quantifiers that has functions. And we can keep writing things like this, right? And so let's say R is a free type variable. So it's a fixed type. So then you have very complicated types that probably can be simplified, but nobody really seems to know exactly how. Yeah, so for example, this one I know how to simplify, and it is just equal to R.
By church? I mean by
No,
UNADA?
the problem is
Or
no,
just
UNADA doesn't work here. Church
No,
encoding
okay.
doesn't work here. This is a church encoding of, if this is f of a, then this is a least fixed point of f of a. Now, can you tell me what that is? And is it even inhabited? But anyway, so this one, for example, is neither UNIDA nor church encoding nor anything else. Well, the reason it's not a church encoding is that this is contravariant in A. And church encodings only work for covariant. So anyway, so I'm trying to build up techniques for this kind of thing because it is useful for certain proofs, but I don't think it has a lot of practical application. So I'm reconsidering that. I will probably just keep it. It's academic. But UNIDA certainly is very useful, and there are so I already had proofs in this text for all the UNIDA stuff. So and yeah, well, unfortunately, I did not manage to finish this chapter already for a long time, and now I'm kind of thinking where to go from here, how to maybe cut scope or you know, put things away and just punt on this entire church encoding business, put it into appendix or something. I need to finish.
You could just take it out and then consider writing volume 2.
Right. Well,
which would just to add to volume 1, not rewrite it or anything.
These 15 pages should be added to volume 1. Right? Something like that.
So a question for the group before we end, where should we, oh, never mind. I guess we, Adrian picked a paper to read for January 6th, I guess. So we're gonna skip doing SOF for one meeting and then come back to it. And when we come back to it, I guess we need to decide where to pick up.
Yeah, well, there's a next chapter. I don't know if you want to pick up somewhere from this chapter. You want to talk
That's
about,
what I'm wondering.
You want to talk about the quantifiers, the UNIDA, existential quantifiers, or UNIDA, or free type classes or something.
Yeah, I mean, today we only got really to here. We didn't go into the different encodings. At least I haven't read that part in any details. So I don't know if we want to pick up here.
Maybe.
I also think chapter 14 with mode transformers is pretty interesting, but maybe we should finish with this first.
No.
What do other people think? Anyone else have an opinion? Where to pick up?
I'm okay spending one more session on chapter 13. I feel like I've got I have more questions. So I'd like to understand it better.
Okay.
But
we can revisit it.
But I'm willing to go with the majority.
No. Chapter on monad transformers is 150 pages.
Yes. So we'll spend a lot of time on that one. But
if you feel like. but I think the free constructions is important. Kind of more general than of more general importance. It could be interesting to formulate this categorically, for example. And I just recently found how to formulate type classes categorically. What is a type class? So type class that satisfies laws. How do you talk about this categorically? Anyway, we can. I think it's if people are interested, let's go on with this chapter now.
Okay.
So that'll be the following meeting. Yeah.
Oh, did you say 13th? 13th or January 6th, Peter?
13th.
I think 13th.
Yeah, good.
Adrian was thinking that maybe people would still be on holiday on the 6th or something.
Well, I will be.
So we're going. Yeah. So we're going to look at the functional collection programming with semi-ring dictionaries paper that you suggested.
Fantastic. That's very interesting.
Okay. Yeah.
On the 13th, right. All right. Well, we're basically.
Will you please?
At the end of our time.
Junicho, could you share the paper or maybe Sergey in the chat? So it is titled functional. How it is titled? This paper?
Yep, I'll put it in the chat.
Great, thank you. Thank you.
Yep.
Thanks.
So grab it before the Zoom ends.
Right.
Otherwise,
so
it's gone.
I got it.
Okay.
All right. Cool.
Answering my own question from the beginning, types in model theory are called sorts. Okay, so we will talk about that.
Yeah, I just had a quick comment on that, Antonio, and that is when people talk about model theory in general, it's heavily weighted to set theory, set theoretic foundation.
Exactly.
And my understanding of Martin Leff's type theory, which is what the other side of type theory is, he's trying to redo it without set theory, but with primitives from bottom up, right? So if you look at Martin Leff's original type theory, you have constructions of types and conjunction and disjunction and all this, and then you build up that in a primitive way without depending on set theoretic machinery. Whereas model theory is historically heavily set theoretic. And so you get into, yeah.
I feel that the definition of models are kind of circular somehow, because what is a set? A set seems to be, or ends to be, a model of a model of set theory, right? So you have this action, but what's a model? A model a model has a new universe, and an universe is a set. So it's kind of a circular definition somehow. So I'm missing something there.
Mhm.
But also in many books or introductory texts, you read that types from type theory, right? For example, are or could be thought as sets. And I'm quite unsatisfied with this introduction. I don't like to think this way because um, it is not the primary construction from type theory, right? It is not
Mhm.
the basement of the theory. So um, I have a feeling of unsatisfaction, or I'm trying to, I feel that I'm missing something at the foundation of every theory, actually. So, okay. But
Yep.
I appreciate, thank you for your comment, Joe. Thank you a lot.
All right. Well, thank you, Sergey, for leading us through this.
Yeah. Yeah. And for writing it in the first place.
Yes.
Yeah.
Yeah, thanks. I mean, it's a fantastic discussion. Thank you. Talk to you later,
Okay.
guys.
All right.
Very
Bye,
interesting.
guys.
All right.
Thanks.
Bye.
Ciao.
Have a happy New Year.
Happy.
Yeah.
Yep.
Happy New Year. Merry
Nice,
Christmas.
everyone.
Bye.
Bye.
Yeah, that too. Yeah.
See you.
Bye.